Hi all, welcome to this discussion on operational amplifiers. In the previous video, we have seen operational amplifiers used as adders in performing some numerical operations and all. So in this video, here we are going to do the numerical integration using operational amplifiers. So this circuit is very important as these were used in previous analog computation systems where it can be used to integrate and find out differential equation solutions. So this is what we are going to learn today. Let's see it. What you are seeing here is the operational amplifier wired as integrator. So you can see in the feedback path, instead of the resistance, we are providing a capacitor. Thus, it's not through the resistance, but instead there is a capacitor. And capacitor, as you all know, it has a frequency response. So whenever any frequencies are moving through a capacitor, it is being opposed by the capacitor using a capacity impedance, and that capacity impedance has a formula of 1 by c omega. So it increases with a decrease in the frequency that you are applying. Let us see what happens when you are applying the virtual ground condition and all for this circuitry. So here you have the virtual ground condition where you can see that the non-inverting terminal is connected to the ground, and as a result of the operational amplifier's action, there will be a feedback system through the capacitor, and still it will be a virtual ground condition on the inverting terminal. Okay, so let us consider two currents. One current is the input current II. So this is II, and the feedback current, that is IF. So this is the feedback current, and the voltage at this point V, I will call it as V2, which is equal to 0 as it is a virtual ground. So that is 0. Alright, so let us see what happens for a current that is flowing through a capacitor. So if there is a voltage difference between a capacitor, then the current that is flowing through it is defined by the equation I is equal to C dV by dt. Okay, and in our case the I is IF, and C itself, and d by dt of V. What is V? V is the potential difference between the two ends of the capacitors. This is one end and this is the other end. So this end is V2 and V2 is 0, and this end is VO, and we have to subtract this point and this point. So V2 minus VO, that is, I should write V2 is 0, so I don't have to write it as 0. So maybe I can write it as 0, and 0 minus VO. So this is what you get. So your feedback current is equal to C minus C dVO by dt. So this is your feedback current. Okay, now let us see what that summing junction happens. What happens to the summing junction? So in the summing junction, your input current II will be equal to the outgoing current IF. And what is II? II is the difference between Vi and V2 divided by the resistance R. So I am substituting that, and as you all know, V2 is equal to 0, so I am not going to write Vi minus V2. Vi minus V2, V2 is 0, so Vi by R, which is equal to, I can take this here, so it becomes minus C dVO by dt, and I can take the dVO by dt to one side, so this is dVO by dt, which is equal to minus 1 by RC Vi. If you integrate on both sides, you get VO. So this integration is over time. So you can integrate your input voltage and get it at the output using an op-amp integrator. It is to be noted that if you are providing your Vi as a DC signal, then the capacitor will not allow this IF to flow through it, because it blocks, a capacitor blocks DC. So this essentially becomes an open circuit. So your feedback path is cut off and nothing is fed back to the input, and as a result the operational amplifier goes to open loop configuration where you have very high gain. So the open loop gain is very high, so as a result the output will go to any of the saturation, either to the positive saturation or to the negative saturation depending upon the input DC voltage. So this is a problem, and you can solve this by using a parallel resistance to the capacitor. So that parallel resistance can be activated when there is no current through the capacitor. Okay, so this is my resistance. I'm going to put that resistance here. So it is parallel to the capacitor. So I have connected the resistance. If your input voltage is DC, then the capacitor blocks DC, but there is a resistance here now, and suppose the value of this resistance is RF, then this operational amplifier will be working as an inverting amplifier with a gain of minus RF by R. So it's not going to any of the saturations. Instead, you can have a fixed DC gain for the operational amplifier if you are providing a parallel high value resistance across the capacitor. So it also regulates the high frequency noises and all. So whenever the input frequency increases, so if you are applying a frequency which is much higher than the normal operating range of this operational amplifier based integrator, then what happens is that that high frequency signals will be short circuited by the capacitor. So nothing will be amplified. So those high frequencies can be short circuited, and the resistance will be shorted by the capacitor, because for high frequency signals the capacitor acts as a short circuit. So there is an upper limit now and a lower limit now for the capacitor based operational amplifier integrator. Okay. So this is the essence of operational amplifier integrators. Now let us see some application of this operational amplifier. Here on the right hand side you can see three kinds of waveforms. The one in the blue color is called a spike waveform because it looks like spike. Okay, so it is a spike train. It has a negative spike, negative spike, positive spike, etc. The second one is a square waveform, and the third one is a triangular waveform. All these three are related to each other by the process of integration. So whenever you are integrating a spike waveform, or whenever you are providing this spike waveform as the input to this circuit, then you will be getting a square waveform like this at the output. And if you are providing the square waveform as the input to this, then you will be getting at the output the third one, that is a triangular waveform. So if you want to change the waveform shape, then this might be a solution for that. And we can see what is happening mathematically here. Suppose the positive side is A and the negative side is minus A, and this one is positive A and this side is negative A. So let it be like this. So you can see here that if you are integrating the square wave from a time t equal to 0 to 1, the period from 0 to 1 is having the positive cycle of the square wave. So when I am integrating that one, then I will be, say, let me say it is VO plus is given by minus 1 by RC integral Vi dt. So I will be substituting it minus 1 by RC integral Vi dt. What is Vi? Vi in the case of 0 to 1 range is A. The function value is A. So I will be writing it as A dt. Okay. So this will give me, so this integration range is from 0 to 1. I am not going to put the limits on, but you can put the limits on. You can see here that this thing is your slope, and the slope is negative. So that is why for the positive pulse or the positive cycle of the square wave, you are having a negative going ramp here at the output. And similarly, you can find out what is happening for the negative cycle of the square wave. That is, this is 2. 1 to 2 minus a dt, and that will give you a by RC times t, and a by RC here is your slope, and this will give you a positive slope. So this portion is generated by this equation. Okay, so this is represented by this portion, and it repeats. Okay, so this is what is happening in the case of integration. And the spike waveforms, when they are integrated, that also will give you a square wave. Spike is a limit short interval pulse. It is also known as Dirac delta, delta function, etc. So you have a negative spike going to an amplitude of minus a within a short interval of time. When you integrate that thing, you will be getting a constant value. So that constant value is represented by this, and you can see this is a negative spike and you are giving it to an inverting amplifier. So negative times negative will give you a positive constant value. So that is why here it is a positive constant value, and here it is a positive spike, but that is being given to an inverting amplifier, so it will give you, I mean, an inverting integrator, so that will give you a negative peak here. So this is how it goes. So from the top to bottom you are integrating. So when you integrate a square wave, you get a triangular wave. So when you integrate a spike waveform, you get a square wave. So when you integrate the spike waveform twice, then you get a triangular waveform. So this is the essence of integration using operational amplifiers. We will see another process, that is the reverse process, that is differentiation using operational amplifier, in another video. So thank you all.